I'm using scikit-learn's Randomprojection method, a technique for dimensionality reduction. It's like shrinking a really big picture into a smaller one, but I'll potentially lose some details in the process. I'm working with a dataset that has a whopping 1,000 features. That's a lot of information to deal with. Dimensionality reduction can make my analysis and model training much more efficient. Let's look at how Randomprojection behaves in this high-dimensional setting. The quiz gives me several claims that I need to evaluate. The randomstate parameter controls the randomness, much like setting a seed in a random number generator. Changing it will give me a completely different projection, which impacts the results. Therefore, this is true. Compared to principal component analysis, PCA, Randomprojection is typically faster, especially for datasets with many features. This is because Randomprojection doesn't need computationally intensive eigenvalue decomposition. This is true. The parameter EPS controls how much dimensionality reduction happens. A smaller EPS value means less reduction, which implies retaining a higher number of dimensions after projection. This is true. That's not true, alas. Randomprojection, by its nature, involves some information loss. It's an approximation, not an exact transformation. Think of it like summarizing a long story. I lose details when I make it shorter. Let's remember that Randomprojection is a powerful, but approximate, method. We use it because it's computationally efficient for high-dimensional data. I'm dealing with a dataset containing 1,000 different characteristics for each data point. That's a lot of information to work with, making it high-dimensional. This is a common scenario in machine learning where using all those features can cause problems. I will use a technique called random projection to reduce the dimensionality of my dataset. It cleverly projects the high-dimensional data onto a lower-dimensional space using random matrices. Think of it like shining a light on a complex object. You're losing some detail, but creating a simpler, manageable shadow. After applying the random projection, I'll have a dataset with fewer features. The goal is to capture most of the important information while reducing computational complexity and improving model performance. This makes my models faster and often improves their accuracy. I'm asking which statements about using the random projection method for dimensionality reduction are correct. Let's see if you know your stuff. This statement is false. Random projection, like most dimensionality reduction methods, inevitably leads to some information loss. It's not a perfect process. We're aiming for a good balance between simplification and accuracy. This statement is true. _random_state is a parameter that controls the randomness of the projection. Using the same value for _random_state ensures that the same projection matrix is used every time, allowing for reproducibility. This is true. Random projection is generally computationally less expensive than principal component analysis, PCA, for high-dimensional datasets because it avoids computationally expensive operations like eigenvalue decomposition. It's a faster, more efficient solution for very large datasets. This statement is also true. The parameter "eps" in scikit-learn's "random_projection" controls the level of dimensionality reduction. A smaller "eps" value leads to less aggressive dimensionality reduction, resulting in a higher dimensional projected space. It's all about how much you want to reduce the data's size. We're exploring scikit-learn's Randomprojection method, a technique used to reduce the number of features, dimensions, in a dataset. Think of it like summarizing a long story. You keep the important parts while leaving out the less crucial details. This is particularly useful when dealing with high-dimensional data, like the 1,000 features in our problem. This question tests your understanding of how Randomprojection works. We'll examine several statements about it and decide if they're true or false. I'm dealing with a dataset that has a massive number of features, 1,000 of them. Imagine trying to build a model with so many characteristics. It would be complicated and computationally expensive. Whoa. That's where dimensionality reduction techniques like random projection come in handy. They help to simplify the data while keeping the most relevant information. The randomstate parameter acts like a seed for a random number generator. It ensures that each time I run the randomprojection with the same randomstate, I'll get the same results. Think of it like following a recipe. If I use the same ingredients and steps, I'll get the same outcome. It helps in reproducibility, a very important aspect of machine learning. Compared to principal component analysis, PCA, randomprojection is computationally much more efficient when dealing with high-dimensional datasets. PCA involves complex calculations, like finding eigenvalues and eigenvectors, which become slow with many features. Randomprojection is faster because it uses random projections instead of these computationally intensive steps. The EPS parameter in randomprojection determines how much dimensionality reduction to apply. A smaller value for EPS means less reduction. The projected space will retain more dimensions and be closer to the original dimensionality. Think of it as zooming in. A smaller zoom factor shows more details. I'm discussing scikit-learn's randomprojection method, a technique used for dimensionality reduction. It's like taking a high-resolution photo and creating a smaller, lower-resolution version of it. You lose some detail but gain speed and sometimes even clarity. This parameter controls how much dimensionality reduction you'll get. A smaller EPS means less reduction. The output will have a higher dimensionality. Think of it as adjusting the resolution of the smaller photo, where a smaller EPS means a higher resolution. We're looking at parameters, which are basically the knobs you can tweak to control the randomprojection process. These parameters allow us to fine-tune our dimensionality reduction for optimal performance. This parameter makes the random projection reproducible. If you set a specific number, you'll always get the same results. If you don't set it, results will vary each time you run it. We're working with a dataset having 1,000 features, which means lots of variables to consider. It's like having 1,000 different measurements for each data point. Wow! Dimensionality reduction helps us simplify this. This is the core technique that takes our high-dimensional data and reduces it to a lower dimension. It works by randomly projecting the data onto a lower dimensional space. This is analogous to changing the viewing angle of the high-resolution photo. This is the outcome of the randomprojection process. We've gone from 1,000 features to fewer, making the data easier to work with. I'm using scikit-learn, a popular Python library for machine learning, and specifically its _random_projection method. This method helps me reduce the number of features, dimensions, in my dataset while trying to preserve as much important information as possible. Random projection is a dimensionality reduction technique. Instead of cleverly choosing which features to keep like other techniques, I randomly project the data into a lower dimensional space. It's like shining a flashlight on a complex object and capturing a simplified shadow, hoping to maintain the essential features. The _random_state parameter helps me control the randomness of the projection. Think of it as setting the seed for a random number generator. I get the same result each time I use the same _random_state value. The _eps parameter controls the level of dimensionality reduction. A smaller epsilon means less reduction, higher dimensionality. I'm working with a dataset that has 1,000 features, meaning each data point has 1,000 measurements. This is a high-dimensional dataset, which can make processing and analysis difficult. After applying the random projection, I have a dataset with fewer features. This makes the data easier to work with, potentially improving model training speed and performance, while minimizing information loss. This is the core question. It's asking us to understand the characteristics and implications of using random projection on high-dimensional datasets, especially in the context of its parameters and computational efficiency. I want to emphasize that this is absolutely false. Random projection inherently loses some information. It's an approximation, not a perfect transformation. This is true. Random underscore state controls the randomness, ensuring that if I use the same random underscore state I get the same results. It's crucial for reproducibility of the experiment. This is generally true, especially for very large datasets. PCA involves complex calculations like eigenvalue decomposition, while random projection is much simpler and faster. Absolutely true. A smaller EPS means I want to reduce the dimensionality less aggressively, so I end up with a higher dimensional projection. I'm dealing with a dataset that has 1,000 different characteristics or features for each data point. This is a high-dimensional dataset, and working with it directly can be computationally expensive and lead to poor model performance due to the curse of dimensionality. That's why I'm exploring dimensionality reduction techniques. After applying a dimensionality reduction technique like random projection, I aim to have a dataset with fewer than 1,000 features. The goal is to keep the important information while reducing noise and computational cost. I'm using a method called random projection to reduce the number of features. It works by projecting the high-dimensional data onto a lower-dimensional space using random matrices. It's a fast and efficient technique, and I'm exploring its properties to see if it's appropriate for the task. The random projection method has parameters that control its behavior. Random underscore state sets the seed for the random number generator. It ensures that I get the same results each time I run the projection with the same seed. The EPS parameter controls the level of dimensionality reduction. A smaller value of EPS results in a less aggressive reduction, keeping more of the original dimensions. This is a multiple-choice question testing my understanding of the random projection method, specifically how its parameters affect the outcome and its computational efficiency compared to other dimensionality reduction techniques such as principal component analysis, PCA. Scikit-learn's random underscore projection is a technique I use to shrink the number of features in a dataset. It's like taking a high-resolution photo and creating a smaller, less detailed version. I'll use random matrices to project my data into a smaller space. And it can be much quicker than other methods like PCA for really large datasets. This question tests my knowledge of random underscore projection in scikit-learn. I need to understand how it works and what parameters I can control. This is a great way to test my understanding. This refers to the size of the data I'm working with, a dataset with 1,000 features. It's a high-dimensional dataset, which is why I'm using random underscore projection It's too big to work with easily. This is the method I'm using to reduce the dimensionality of my dataset. I'm projecting it from a high-dimensional space to a lower-dimensional one, hoping to improve my model's performance and make things faster. This is a smart approach. This is a parameter in random underscore projection I use it to set a seed for the random number generator. This lets me reproduce my results exactly if I run the code again, ensuring consistency. Think of it as setting the randomness to be controlled, not completely random. This parameter controls how much dimensionality reduction I do. A smaller value of EPS means I keep more dimensions, less reduction. A larger EPS means I reduce the dimensions more aggressively. It's a trade-off between accuracy and simplicity. These are the settings we adjust to control the behavior of random underscore projection For example, random underscore state and EPS are parameters. I can fine-tune these to get the best results.